So we continue our discussion about in transport phenomena. So we are in the book of the BSL. We are in the chapter 1. Chapter 1 is talk about the viscosity and the mechanism of the momentum transport. And here, as talk about the viscous flow, viscous fluids, uh, uh, the definition of the viscosity is the resistance of the any to flow of the any fluids in the system. Uh, we are in here we are going to talk about the Newton's law of viscosity or molecular transport of momentum. Let's consider any system two plates, the upper one and the lower one. Distance between two plates is y. When the time is the less than 0, the fluid is in between these two plates is in the rest, it's not moving. So but the time t, you are starting um, applying some force F and the lower plate by the constant velocity of V. After certain time, because of the lower plate is moving by some constant velocity of V, you will see some velocity profile distribution like this in unsteady state flow is Vx. We are here just talking Vx velocity, not Vy and Vz. We consider are zero. This Vx is function of the y and the t. After a certain time later, enough time, we will see the velocity profile like this in here. We call this type of distribution in steady state the laminar velocity profile, because the flow is called laminar because layers are is pass from this layer to another layer. You pass in some order. If you see this order some inside of some velocity profile, you call this nominal flow. In other case, if you see some chaos in your velocity profile, we call this turbulence flow. So the force actually acting on the lower plates per area, we call this the stress acting on the fluids, is equal to mu v over y. In here, the mu is, shows the the viscosity of the fluid, and v is the constant velocity of the plate here. Then, if I exchange F over A by the symbol del1, which is the force in the x direction, and it is perpendicular the y direction, then it's understood that this is the force exerted by the fluid of the lesser y on the fluid of the greater y. Then also if I replace the v over y by the minus dvx by dy y dvx, because we just consider here the velocity profile in the x direction vx, then in terms of the symbols I can write this equation by this equation here. This equation states the shearing force per unit area is proportional to the negative of the velocity gradient, is often called Newton's laws of viscosity. It has been found that the resistance to flow of the gases and all the liquids which molecular weight less than about 5,000 is described in this equation. And this equation is called the Newtonian fluids. Other case, like such as polymeric liquids and suspension and other type of complex fluids, are not described by this. We cannot describe this kind of fluid by this equation. That's why we call them non-Newtonian fluids. In here, this term may be also interpreted as a flux of the x momentum in the positive y direction. Before we define it like a force acting on the x direction perpendicular to the y direction, now we can say is flux of the x momentum in the positive y direction, where the term flux means the flow per unit area. So another definition is the quantities, that one is mu over rho, density of the fluid between these two plates. It can be defined the kinematic viscosity. So when we move this table, summary of all the units. This term is represent the Pascal F over A unit area is shear stress acting on the fluid, and Vx is the velocity of the fluid in between two plates is meter per second. Y distance between two plates. Mu is the viscosity Pascal second. Kinematic viscosity is the meter square per second. So in this chapter 1, you can see some tables. This gives some viscosity of the water and the air at the 1 atm, because your viscosity is the function of temperature and pressure, or viscosity change in a fluid by the change of the temperature and the pressure. Some viscosity or some gas and liquids at the atmospheric pressure. Okay, some conditions, so on. You can find the viscosity of the many fluids on the literature actually. So the topic is the generalization of the Newton's law of viscosity. In the first example, we just consider the actually velocity profile of the fluid in between two plates on the x direction. So we just obtain just one component of the viscosity, just Vx, but others Vy and in the Vz sets are zero. But in many cases, we can find the velocity of the fluid can be dependent on the x, y, z direction all the end time. So for any velocity, any fluid has some three elements, as we know before. These are Vx, Vy, and Vz. Also, your Vx component can be dependent x, y, z direction. Vy can be dependent x, y, z direction. Vz can be dependent Vz, x, y, z, and t direction. This has some 9 elements in terms of the coordinates, and we call this tensor. In such situation, there will be 9 stress components like this. So in this figure, let's say we have some let's say two plates. There is some fluids between these two, and you have some control volume. Let's say like this, and you pick some differential volume, and this differential volume, let's say, is some differential surface like ds. So the center of this differential volume can be represented x, y, z, and this differential volume you see from here has some three surfaces. The first one is in the x direction, second one is in the y direction, the first one is the x, second one in the y direction, the third one is in the z direction. So actually there are two types of forces acting on your fluid. The first one is the pressure forces acting on fluid. This pressure force always has to be perpendicular to the surface. Like here, that one can be obtained. The pressure is acting on force acting on the x direction. In here, that one is the unit vector. Also, the second one is the viscous forces acting on your fluid, and this show the viscous force. The viscous force not necessarily the acting on the surface by the 90 degree or not perpendicular. It has some angle. This is normal vector, and this is some angle, the normal vector, and this has some. That's why, because of this has some angle, this has some three elements x, y, z for the first surface. For the second surface, the pressure is acting perpendicular the y direction, and the viscous force acting some y. This surface area has also three elements. Also similarly, the pressure acting on the z direction surface, and viscous forces. So okay, when we move in the next parts, actually In next part, you see from here, we define all these forces acting per unit area, that one, and also that one. Each of these has components, these three components. As a finally, um, for the sum of forces per unit area, stresses and pressure, because of pressure and the viscous stresses. And finally, can define molecular stresses by this notation. Like here, in here, I and J may be X, Y, Z. We know that one is the Kronecker delta, which is the one if the I equal to J and the zero if the I not equal to J. Then this has also two physical interpretation. The first one, the force is acting on the J direction on unit area perpendicular to the I direction. And the second one, flux of J momentum in the positive I direction. So in the stress, that one, this shown here, that's the formula. Sorry. Okay. That one here, that one is called normal stresses. Other quantities like these are equal each other, and these are equal to, they are called shear stresses. Two kind of stresses is normal and shear. So we continue that in this table we can summarize our components of molecular stress tensor, because we have 9 elements. Molecular momentum flux for the x direction, as we show in the above. This is, sorry, this x, z, y. We have some control volume like this, and so on. The for the x direction, like this direction, the vector force per unit area acting on the shaded area in the first one, in the like this x direction, like in this direction, we call by this term. This comes from pressure forces. This comes from the viscous forces, but because this viscous forces not perpendicular to the surface, not necessary, then it has three elements. For x component, that one; for y component, that one; for z component, that one. For the y direction, actually, for the shaded area, similarly we have that one because of pressure, because of the viscous. This has also three elements. The first one is equal to that one. In here we don't have any pressure because pressure is perpendicular to the surface, and that one, in here we just have the pressure here because pressure has to be perpendicular to the surface, the others they don't. Similarly, and in the z direction for the xyz components, and we have the pressure term here, so we call here the tensor stress tensor by 9 elements. Okay, if we just continue our discussion, okay, we know from the above this term is equal to that term. Okay, also um, we know we have that one, the b. We have just finally we can obtain that result Okay. In here we can write, instead of I, we can just replace by this formula, and also by B is equal to del 1. In here the K is called dilatational viscosity. It's coming from the kinetic theory. So anyway, finally we obtain that form. From here we can just go the vector tensor notation like here. So we can write uh, stress tensor, stress force acting on the body by this formula. In here, that is the unit tensor. Here has some components, and this is the velocity gradient tensor. That one, and this is the transport of the velocity gradient tensor. Okay, and this is the divergence of the velocity vector. So from here, these are generalize the Newton law of viscosity we obtain for any fluid is this general. The important conclusion is that we have generalized of the in the first equation, in the first part, the definition of velocity. This generalization involves not one but two coefficients characterizing the fluid, the viscosity mu and dilatational viscosity K. These two things characterize the fluids, give some specific characterization. Usually in solving the fluid dynamics problems, it's not necessary to know this term, because if the fluid is gas, we often assume it to act as an ideal monoatomic gas for which K is identical to 0. If the fluid is liquid, we often assume that is the incompressible, and in chapter 3 we show that for incompressible liquids this term is then gives 0, this cancel. So okay, if the gas is monoatomic gas, then ideal monoatomic gas, then this term is 0. Okay, if the liquid is often incompressible, then we assume that divergence of V, then it gives the result of 0, then we cancel that term from here. And dilatation of viscosity is important in describing the sound absorption in the polyatomic gases and in describing the fluid dynamics of liquid containing gas bubbles, so on. So okay, so this is the final equation we obtain in this chapter, and the sign convention for the stress tensor. Okay, so we emphasize in the connection with first equation we in the first part, that is the force in the position x direction, the plane perpendicular to y direction. We defined this before, and that is the force exerted by the fluid in the region of the lesser y on the fluid of the greater y. In most fluid dynamics and the elasticity books, the word lesser and the greater are interchanged and is written in this form. The advantage of the sign convention is these books are the sign convention used in the Newton's law of viscosity is consistent with that used in the Fourier's law of heat conduction and Fick's law of diffusion. The sign convention for that one is the same as that the convective momentum flux, that one in 1/7 and table, so on. So anyways, continue. Okay, in this chapters in the section 1.3 give the pressure and temperature depends on the viscosity. You can see from here how the viscosity depends on the viscosity and temperature, and molecular theory of the viscosity of the gas at the low density. Another section you can find here. Okay, you can go and read from the chapter 1, and you can check all this equation and where they come from, and molecular theory of the viscosity of the liquids, like here, and viscosity of suspension and emulsion, and so another one is the convective momentum transport. In the first part, we were talking about the actually molecular transports and the set of quantities. We defined all these terms, the flux of the J momentum across the surface perpendicular to the I direction. Then the related is the velocity gradient and the pressure, and we found that this relation involved two material parameters, mu and k, so on. Momentum can, in addition, be transported by the bulk flow of the fluid, and this process is called convective transport. If any transportation happens by the molecular, we call this molecular transport, but if happen in the bulk flow of the fluid, we call this uh, transportation in here. Momentum is called convective transport. Um, Actually, the convective transport uh, in here as a final can be shown by that. This has the 9 components. In the x direction, you see it's that one, and this has 3 components. And y in the y direction, that one is 3 component, and z as you see from 3 component, and it's totally convective. It's called second order tensor. That one called convective momentum flux tensor from the definition. Similarly, so then finally the any combine combine uh, combine momentum flux, which is the sum of the molecular momentum here and sum of the convective momentum here. We can write this in the open form like this. Then also we call this convective sorry, not convective, combined momentum flux here. So we can write this is this. So we are gonna use that one, and later after discussion of this book, this is combined momentum flux and so on. Okay, summary of the notation of momentum flux. This gives the convective momentum flux tensor because it's a second order tensor have 9 elements. This gives viscous momentum flux tensor has also 9 elements. This molecular momentum flux tensor has some 9 elements, and combined momentum flux tensor, this has also 9 elements, second order tensor. So this is the end of the chapter 1, and we will continue our discussion by chapter 3 in the next video.